Hi everybody. In this video, we are going to refine our limit skills a little bit and talk about something called one-sided limits. So the notation for one-sided limits, as opposed to two-sided limits, which is what we introduced in the previous video, is really similar, but there's a little difference, of course. So we have a two-sided limit coming from two different sides, approaching, for example, 2 in the previous video. X is approaching 2. You can approach 2 from what we'll call the left side if you're using numbers that are less than 2 to approach 2, or the right side if you're using numbers that are larger than 2 to approach 2. So we can kind of split a two-sided limit up into the limits from one side. Okay, so the notation looks really similar. Okay, we still have lim, we still have x approaching some number. We still have f of x, the function next to it. And if we are approaching a number, in this case c we're using, from one side, let's say the right side, we're going to use a plus. Kind of in the exponent, but it's not really an exponent, it's more like a superscript. So when we have a plus after the number, this is called the right-sided limit, or the right-handed limit. Okay, so what it means is we're going to let x approach c, but with numbers that are larger than c. And it's a little bit confusing because graphically what's going to happen is that we're going to be coming from the right, but we're going to be moving towards the left. So we have to just kind of get some practice with, with which one is which. So a right-sided limit comes from the right-hand side approaching C. So in the other case, when we have a left-sided limit, we put a minus, again, in like the superscript or like next to the C, but up in like the exponent position. Okay, and this would be called the left-sided limit or the left-handed limit. And we still let x approach C, but now with numbers that are less than C or smaller than C. And again, it's called left-sided, but we are going to be coming from the left and moving towards the right when we're finding it. So we are clear about that. We'll just note here coming from the left. I mean, we had to choose one to make it so this is just the standard way. So if we have like a picture, I'll just move this over a little bit this way. Let's make some axes here, x and y, and say that we have a function like maybe here is c. We have a function that maybe looks something like this. It's split up into two different pieces. This is called the piecewise function. We'll look at examples with this, but you can see from one side, as you're approaching c, the y values or the heights of the function are doing different things. So as you approach c from the right-hand side, that would be going towards c, coming from the right, so this direction. And so we go along the graph and we just kind of see, okay, I'm going towards c, but from the right, I'm using numbers larger than c on the number line. And so, the y value of what we are approaching as we approach c this way is right up here. And so we'll just call this something to stick in our definition here. So let's just call this L for limit. So we would say that this equals L over here. And graphically, that's what that would look like. If we're approaching from the left, or you're looking at the left-sided limit or the left-handed limit, as x approaches c, we're going to go towards c from this side. And again, we're marching along the function. We can ignore everything to the right of c, and we're just looking at what happens as we approach x equals c. from the left-hand side. So we're looking along the function this way. And it looks like that if, even though there's a hole there on this bottom part of the graph, that the y values are heading towards whatever this number is. And that might be different, so we'll call that m. Okay, so graphically, you might have a different limit from one side or the left, from one side or the other. They could match up, and that's okay too. Sometimes they don't. The connection with this and the two-sided limits is that in order to have a value for a two-sided limit, these both have to be approaching the same point. So they have to kind of be meeting together in order for the two-sided limit to exist. Okay, so this is a little note here. The two-sided limit, okay, the limit just without any plus or minus in it, we would say that it exists or has a value if and only if the one-sided limits are equal. And in symbols, we would write that like this, and kind of thinking about it in the opposite way. We can also say that if the two-sided limits, the two one-sided limits don't equal each other, then the two-sided limit doesn't exist. Okay, so we'd say if the limit as x approaches c from the right of the function does not equal the limit as x approaches c from the other side, from the left side of f of x, then the two-sided limit, the limit as x just approaches c from both sides, does not exist. And we can abbreviate that as DNE. Okay, so for example, let's look at the limit as x approaches 0 of the absolute value of x divided by x. So if we try the first thing, if we kind of just go down our list, we'll look at several different ways of seeing what the limit here is. The first thing we should always try is direct substitution. So if we plug in x equals 0, remember the way that we're going to indicate that is with a ds above the equal sign. Okay, we get the absolute value of 0 divided by 0. Absolute value of 0 is 0, so we get 0 over 0. And remember that this is undefined. But when we're plugging things in to find a limit, when we get 0 over 0, it really means do more work. Like this will never be the answer to our limit. It means we have to investigate a little bit further. So there's not really any algebra to do here to kind of get rid of the absolute value or anything. So I would suggest whenever you have an absolute value in the limit to look at either a graph or numerically. So let's take a look at what each of those methods will look like. So numerically. Remember, this means plugging in some numbers, making like a chart. Okay, so we're going to do x up top. We'll do f of x in the bottom, and that's just the absolute value of x divided by x. So you can write f of x here, or y, or the function that we are plugging into. So we're trying to find the two-sided limit, so we're going to put 0 in the middle. And we need some numbers that are a little bit less than 0. So just a little bit negative. So I might start with like negative 0.1. Then a little bit closer to 0 might be negative 0.1. And then a little bit even closer might be negative 0.001. Okay, when we plug in the values that we have here, so if you're not sure where to find the absolute value in your calculator, it depends on what calculator you have. But if you have like a TI-80 384 or something along those lines, it's under the math button, which is like halfway down on the left-hand side. Then you just hit the right arrow over to get to num. Then it should be the first option. It should either look like ABS and then parentheses, or maybe you have a newer calculator and it actually has the absolute value bars. Okay, so take a look at your calculator, go get it, and see if you can find the absolute value button. And if not, you can either do some Googling or we can talk about where it is on your calculator. So when you plug in negative 0.1, this should come out to be negative 1. When you plug in negative 0.01, you get negative 1 again. And when you plug in negative 0.01, you also get negative 1. Okay, so if we just take a look at this, we can even just shade this out because right, that's undefined, so we can't actually plug a 0 in. So as x is approaching 0 from the left-hand side, okay, so we've got a left-sided limit here. So x is approaching 0 from the left. The y values, what's going on here is, well, they're not getting closer and closer to anything, but they're just staying constant. And when that happens, that's the limit. Okay, so the y values here are approaching negative 1. So we would write the limit as x approaches 0 from the left-hand side, so with a minus there, of the absolute value of x over x, that is equal to negative 1. Okay, let's look from the other side. So a number that's a little bit bigger than 0 might be just 0.1. So we'll put that over on the far end because remember we want to get closer to 0 here. Oh, I'm not being consistent with my colors. I think I was using blue for this. Not a big deal, but I'd like to stay consistent with that. So let's change this to blue. Oop. All right. Then a number that's a little bit closer to 0 but bigger than 0 might be 0.01. And then 0.001. Okay, so here we are approaching 0, but from the right-hand side. So numbers that are bigger than 0, right? So go ahead and again plug these into your calculator. And you should find that you'll get positive 1 for all of them. And again, the limit as x approaches 0 from the right, even though we have 1, 1, 1, right, it's just going to keep staying at 1 no matter what we choose to plug in, even if we get closer and closer to 0. So on this side, we would say the limit as x approaches 0 from the right-hand side of the absolute value of x over x, that is equal to positive 1. And so here we have a case where these are not equal to each other, right? They're doing different things from different sides of 0. And so when you have this situation, okay, these are not equal. So the two-sided limit, we would say, does not exist. And this is how we show a limit does not exist. We have to look at the limit from both sides and show that they're not the same. Right here we have negative 1 from one side and positive 1 from the other. So they're not heading towards the same thing. So we say that the two-sided limit does not exist. You can also see this graphically. So you can, if you have a graphing calculator, you can use the same thing as finding the ABS in your menu and plugging in just x instead, closing the parentheses, and then hit divided by x in your y equals. And you should get a graph of this. Okay, and what the graph looks like. It's got two pieces to it. And they are horizontal lines. So we have one piece that's down here at negative 1. And again, your calculator won't show you this hole here, but remember we can't plug in 0. So there's going to be like a hole in the graph, right? So, but all up until we get to x equals 0, which again is on the the y-axis here, Right, this is x equals 0, so we're approaching 0 from the left. Okay, here we had -1. Then from the right, as we approach 0, it was all positive ones. We have a horizontal line up here at 1 with an open circle there. Okay, and again, you can kind of see how, right, this kind of table looks in a graph, right? So we can actually put those here as well. So here's the side you would look at from the left-hand side. And then here's the side you would look at from the right-hand side. And since there's this like gap or this jump in the graph, and again, I should be clear, like we're looking right here, right? That's where we're looking. Then we would say that the two-sided limit does not exist. Okay, so we'll say jump in graph. Two-sided limit, limit as x approaches 0, of the absolute value of x over x, not equals d/any, but just is d/any. So we'll just write that. Okay, so things with absolute values in them tend to have this behavior where they have a jump at some point, because absolute value will change whether you have a positive or a negative thing in it. So this is something that can happen typically with absolute value stuff. Another kind of function that has some jumps in it is what's called a piecewise function. So here's an example of that. We're going to find the limit as x approaches 1 of f of x, where f of x is this piecewise function. So we have this curly brace to indicate that we're talking about a piecewise function. And what they are, they're functions that have maybe 2 or even more different rules or different parts for different x values or different parts of their domain. So for some x values, we're going to be following this quadratic or this parabola, right? If x is greater than or equal to 1, this is the rule we're using. And if x is less than 1, then we're going to be following this line. Okay, so I don't know, I would suggest actually a graphical method for this. So let's just, and this is a good review for like graphing things as well. So let's see what happens when we try to graph this. Your calculator is going to be kind of hard to graph this with unless you know how to do it. It's a little hard to explain. So I wouldn't rely on your calculator much for piecewise functions. If you do put both of these pieces here and here in for y1 and then y2, they're going to overlap together on the graph, and that's not what this graph looks like, right? It's going to have half of it, or part of it will be a parabola, and the other part will be a line, right? And it's going to split right at 1. So it's going to put like, let's see, label our axes here. I'm going to put 1 here. We only need to go out a little bit further in either direction. So let's just go out to -1 on one side and then maybe 3 on the other. Okay, and then for the line, right, that's going to be everything that's less than 1. So from, right, so it's going to like kind of be splitting here. And the line is going to be on this side, right? That's x less than 1. And then the parabola or the quadratic, that's going to be on this side, right? That's x greater than or equal to 1. And we'll have to pay attention when we actually, with the equality, when we actually figure out what the points are. So I would actually set this up with a chart and just plug in some numbers and plot them. So let's do the parabola first. Let's do x squared minus 6x plus 7. And remember that this is only for x greater than or equal to 1. So I'm going to start with like 1 and then 2 and 3, and that should be enough to kind of see the shape. So we're going to plug a 1 into this function for x. So we'll do 1 squared minus 6 times 1 plus 7. All right, that comes out to be 2. Okay, we'll plug a 2 in, 2 squared minus 6 times 2 plus 7. And that comes out to be -1. And we'll plug in a 3. And that comes out to be -2. Okay, now here's where the equality matters. So like we have when x actually is equal to 1, we're following this parabola or this quadratic. So this is going to be a filled in circle or a filled in like point, whereas on the line it's going to be an open circle or an open point. So when we plot these, let's see, I'm going to need some like scale on my y-axis here. So why don't we just go up to like 3 and down to -3. Okay, so we have the point 1, 2. And again, this is filled in because it's on the parabola when x equals 1. We've got 2, -1. Okay, so that's like, oh, my label is going to get in the way. Let's just put that up here. 2, -1 is right here. And then I'll move the 3 up here as well. Then we've got 3, -2. All right, so we don't have the full picture of it, but we know the shape of a parabola. So it might look something like this and then, kind of turn around again. So there's that half of the graph. The other part is that line. So let's also set up a chart. Now we're going to be looking with x values that are less than 1. So maybe we should do, like -1, 0, and 1, and that should be enough to see what's going on as x approaches 1. Okay, so we'll plug in -1, -1 minus 2, that's -3. 0 minus 2, that's -2. 1 minus 2, that's -1. Okay, and we're going to have an open circle when we actually get to x equals 1 on this part of the graph. All right, so let's see, -1, -3, so that's this point. 0, -2, that's this point. And then 1, -1, I'm just going to move my label up here. That's going to be an open circle right there. And there's the graph of that piece. So now you can see from the graph, right, there's a jump here, right? So as we approach 1 from one side, the y values are heading towards 2. And as we approach 1 from the other side, the y values are heading towards -1. The y values, come on. All right. So the limit will be does not exist, or DNE, but let's kind of notate that. Excuse me. So from the right-hand side, right, we're going to be heading along the function as x approaches 1 from this direction. And we just look and see, okay, the y values are getting closer and closer and closer to the y value of 2. And so that is what we will write here. Let's write the limit as x approaches 1 from the right of f of x is equal to +2. On the other hand, the limit as x approaches 1 from the left, right, as we march along the function here, remember that the limit does not see what's happening at the point. We don't care when we're finding the limit. We're just approaching x equals 1, but we never actually get there. So you can actually just cover up like what is happening at 1, and you just see, okay, if I didn't know any better that there's a hole there, what would the y values be heading towards? Right, and of course that is -1. Okay, so from this side, we would say the limit as x approaches 1 from the left of f of x, that's -1 right here. Right, and the +2 up there. So because these aren't equal to each other, we have to write that the limit as x approaches 1 of f of x does not exist. I don't think that this is the case with any kind of absolute value function or any kind of piecewise function, because if this line were maybe moved up a couple, just like shifted vertically up, we could have a situation where it would exist. Like if they met together, then that would be fine. Even though it's kind of sharp there, that's no problem. They're heading towards the same point. Okay, so it's really important to actually graph these out and see what's happening at the point. So that is it for one-sided limits for now. Tune into the next video and we will look at a bigger graph and just practice finding limits graphically.